boys and girls, welcome to Lynn's Lab Coat, and we are going to do some science experiments today. Before we start our science experiments, I would like you to watch a video from Cirque, and it's about dancing raisins. Now once you've watched the video, I'm going to come back on and say a few more words, and we're going to do some experiments together, and then at the end of our video we will discuss our results and our predictions.
Hi, my name's Ollie.
And I'm Ewan. I'm part of the early years and primary team here at Cirque. And today we're going to do
Dancing raisins.
For this activity you need
Some lemonade and some raisins.
Simple.
Simple!
Okay, so first thing we do is open the bottle of our lemonade
We just got one already.
and pop some raisins in. And Ollie is going to tell you what he notices when he puts the raisins in.
But they sink to the bottom and then they go back up. And they make little bubbles.
There's lots of bubbles appear,
Yeah,
and they sink to the bottom and then they float up to the top.
I put loads in, loads of bubbles come.
So as Ollie rightly said, the raisin is sinking to the bottom and then it's floating up to the top. But why is it floating up to the top? Well, the wrinkly skin on the raisin is allowing the carbon dioxide bubbles inside the lemonade to attach themselves to the skin, and then acting like a little bit of a buoyancy vest, you know, a safety jacket or armbands, it's bringing the raisin up to the top. When it gets to the top, the bubbles are popping, and then what happens to the raisin once the bubbles pop? They sink back down, correct. So, what we've noticed when we added the raisins into the bottle of lemonade was that the number of visible bubbles increased. Do we know what the name for these bubbles is? What gas these bubbles are, Ollie?
CO2.
Very good. CO2, or carbon dioxide. Now, we're not producing more carbon dioxide bubbles when we put the raisins into the bottle. It's that the carbon dioxide gas is already in the solution. And when the raisins go into the bottle, we are releasing those bubbles from the solution. This is a physical reaction called nucleation. Isn't it interesting?
Yep.
Looking forward to you sharing your videos with us on Facebook and Twitter. See you next time.
Bye.
Bye. Does the other dried fruits work just as well as raisins in the bottle of lemonade? Something that you could investigate further is how long does it take for the raisins to stop dancing, where you could either use a video on a mobile device or just time it with a stopwatch. You could also take two equal-sized grapes, and if you peel one of them and put both of them into a bottle of lemonade, what do you observe? Prior to you doing this, you could predict what you think might happen. Does the peeled grape or the grape with the skin left on affect the buoyancy in any way? And why don't you investigate or research a little bit more about nucleation online? Please do share your findings, your videos or your photographs of the children in your care taking part in this investigation with us at Cirque Primary, or at Cirque Primary on Twitter, or at Cirque Primary on Facebook.
Good morning, boys and girls. Welcome to Lynn's Lab Coat. Now, those of you who've had me as a teacher know that when I'm wearing my lab coat, we are going to do some amazing science. And you know me as Mrs. Richmond. But Lynn's Lab Coat is our series of science videos. Now, you've just watched the video about the dancing raisins. Now, I don't have any raisins, but we're going to do a similar experiment today with some of the things, and we're going to do some, not a demonstration, we're actually going to have an experiment to try different things to see what happens. So, behind me here, I've got all my equipment I need. I actually don't have little bottles of lemonade, but I've got little bottles of fizzy water, and I've got some glasses to pour in some lemonade in. I'm a bit worried about lemonade, boys, because it has actually been open, and if you look at this space here, any of the carbon dioxide gas in the lemonade may have actually come out of the lemonade into the space here, and when I open it, the carbon dioxide will escape, so there won't be so much carbon dioxide in the lemonade solution. So I'm a wee bit worried that wouldn't work. So as a backup, what I've got is I've got some cans of 7-Up, which I know will still have the carbon dioxide in, as they'll still be quite fizzy. So that's what I've got with me. I've also got, I don't have any raisins, but I've got some other things that the Cirque video suggested we could try. We have got some grapes. I've got a peeled grape, and I've got an unpeeled grape and a peeled grape, because that's what we're going to try and see which one is different. I've also got some, don't know if you know what these are here. I've also got some, not raisins, maybe tell by the colour, some cranberries to try, and I've also got something which I thought would be quite interesting. I've got some kiwi fruit. Now, with the kiwi fruit, obviously the inside of the kiwi fruit is quite soft, quite smooth, and the skin of the kiwi fruit is really rough and hairy. So I actually thought that would be a good experiment to try to see if the inside or the skin of the kiwi fruit would be any different. So let's have a wee think what to do first. I think the first thing I would like to do is do an experiment to see if it makes any difference with the grapes, whether they're peeled or not peeled. Because remember, when you're doing a science experiment, you change one thing. So I'm going to do my grapes both in the fizzy water. Move everything back. The fizzy water is in the same size of bottle. My grapes are the same size. But the experiment I'm doing, I've got one difference only, and the experiment I'm doing is to see whether it makes a difference if the grapes are peeled. Because in an experiment you only change one thing. Everything else is exactly the same. Because if you've got more than one thing different, you don't know if that's what makes the change, basically. So you only keep one thing, make one thing different. So let's open my fizzy water. Now you can see the carbon dioxide bubbles coming up there as I open it, so we know they're quite fizzy. And at the same time, I'm going to drop my grapes in. Now, before we drop them in, we should actually predict what we think is going to happen. Now, after watching the Cirque video, I know he used raisins, and raisins are quite bumpy. And the raisins dance around, the carbon dioxide hung onto the sides of attached itself onto the sides of the raisins, and the raisins danced up and down. Now, when I'm looking at this, my prediction is with this grape here that's not peeled, it's really smooth. I don't think much carbon dioxide is going to attach to the side of that grape. But this grape here, I don't know if you can see, this grape here is actually really bumpy. So I'm predicting this one will dance more because more of the carbon dioxide will get on it. So we'll drop them in. 3, 2, 1, and we'll see what happens. 3, 2, 1. Now, if we look what... now, interestingly, the smooth grape came up to the surface first, and that's actually almost opposite what I thought. I thought the grape with the no skin would actually dance more. Now, so we can see, you can see the carbon dioxide bubbles on the grape. It looks still as if, to me, as if this one with no skin, this one with the skin is actually going to dance more. It's certainly got more of the carbon dioxide on it. You can see the bubbles. I actually can't see any carbon dioxide bubbles on the peeled grape at all. Now, I wonder why it's trying to dance. Look, it's trying to get up, but it's just not managing to get up. I wonder if you can give me a reason why you think that isn't actually dancing there. Do you think it could be anything to do with the weight? I think I might have been better trying half a grape. I wonder actually even if I could... I wonder if this would work actually if I left you for a second to get another grape and just put in that. You continue watching this and I'll talk to you when I'm going over and I'll get another grape. Now, this time I'm going to do the exact same thing again. I hope there's still some carbon dioxide left, but I'm actually not even having, I'm going to do 1/4 of a grape, because I think my prediction was wrong for a start. It looks as if the unpeeled grape is worse than the peeled grape. I thought the unpeeled grape would actually be better at jumping around, but I think the weight of them is too much for it to jump. So what I'm doing is I'm using 1/4 of a grape so they're lighter. I've got the peeled one, I'm going to put in the same bottle, and the unpeeled one, and let us see if this makes a difference. We'll put it in, let's hope there's still enough left. Let's see what happens this time. Aha, yep, we can now, can we see? It's definitely, oh, there, yep, it's definitely trying to move around more. And I can't believe the peeled grape is actually not doing anything. Now it may still be too heavy, so I can even cut, I wonder if I can even go, so this is a good lesson in fractions. That was 1/4 of a grape. I wonder if I did the exact same experiment again with 1/8 of a grape, whether they'd be light enough to actually start dancing around. Wait till we see, but definitely for some reason, and I'll have to think about this afterwards, some reason the unpeeled grape, the one with the normal skin, oh there it comes, is actually better, which completely contradicts what I thought. That's 1/8 of a grape in this time, which is lighter. The peeled grapes are doing almost nothing at all. The unpeeled grapes, as we can see, are beginning to dance around. So the carbon dioxide is adhering, it's sticking onto the side of the unpeeled grapes and actually making it rise and fall. So I'll leave that to the side. Let's leave that there. And that is really interesting. I'm actually going to have to think why that is, because I really don't know. Oh, now, Mr. Richmond's actually, Mr. Richmond, I don't know if he's right. Mr. Richmond is mouthing something at me here, and he's saying acid. Do we think he's right? I think he thinks that this one's more acidic. I'm not sure. We'll have a think about that. But I think that's very strange. Now, let's have a wee look here. Now remember I said that an experiment you just make one difference. So I think what I'm going to try this time is I'm going to use my beakers here, and I'm going to see whether there's a difference with lemonade to fizzy water. So what I need to do is pour the exact same amount of lemonade and water in both the glasses. I'm not going to measure it out, I'm just going to roughly take, well, more than roughly take where the volume is, and I'm actually going to use a cranberry, or maybe 2 cranberries in each of the beakers. So my fruit is the same, my beakers are the same, I'm going to have the same volume of liquid in. The only difference to make it, it's called a fair experiment, boys and girls. For a fair experiment, as I say, you only change one thing, and I'm going to put in a different solution and see whether lemonade is better or the water is better. Now, if one is better and makes it dance more, why would that be, do you think? Carbon dioxide, isn't it? So if one makes them dance more, it must have more carbon dioxide. So if we were predicting, do you think the lemonade or the water has more carbon dioxide? I want to say the lemonade. I know my husband thinks no difference at all. So I wonder if you can tell him by pouring it out. So when I'm pouring it out, to me it looks as if the lemonade is fizzier. It looks, now, look at there's a problem right away. Like I said, it has to be the same volume. I'm just going to pour some of that out because it's got to be the same volume. A wee bit more again. Because remember, if the volume's different, I don't know whether that's because of the difference. Right, I think that's near enough. So, I've got 2 cranberries. I'm going to drop them in. My prediction, which we know my prediction was wrong with the grapes, my prediction is that the lemonade is going to make them dance more than the water. Drop them in and we'll see. Now remember what the set video said, that when the carbon dioxide adheres to the surface and makes them rise to the top, and when the carbon dioxide bubbles burst, then they use raisins, but our cranberries should sink back down to the bottom again. So, interestingly, ours are not really doing any sinking, but there it go. Now, I think that looks as if my prediction is right. To me, when I'm looking at this, instantly, to me it looks as if there's more happening in the lemonade than there is in the water. And I'm taking that as a result that the lemonade has more carbon dioxide in than the water. Because look at the difference between the two. I wonder if I can, yeah, it does. So these are moving a bit, but nothing like, for some reason, I don't know why this one, there we go, it doesn't seem to do, so that they're both doing, oh, interestingly, this one's now gone a bit crazy. Again, I'm not sure Mr. Richmond's agreeing with me, but we'll think of the results after a video. But I am thinking at the moment, and now I say go back and think of the results, and we'll sort of have a wee discussion, and we'll have but I think it looks to me as if the lemonade has more carbon dioxide. There's more carbon dioxide adhering onto the side of the raisins. Right, let's have a wee think about our results. Before we think about our results, I wanted to show you this here. This is a picture of an image of carbon dioxide, just so we can talk about that, because we spoke about carbon dioxide gas and we knew how that's why the raisins were dancing, or the cranberries were dancing, or the grapes were dancing. We spoke about how the gas was adhering or sticking onto the surface of them, and because the gas is lighter than the water, is less dense gas, the atoms are spaced out more, so the gas floats in water because it's less dense. So because the gas is lighter, when the carbon dioxide gas adhered in bubbles onto the sides of the surface of the fruit, it rose to the top. So this is just to show you what carbon dioxide looks like, and you can see, or maybe you can't see, but I'm telling you, it's called carbon dioxide. The prefix di means two, so it literally means carbon to oxygens, and that's what it means. And you can see here the grey molecule, or the grey atom is carbon, and the red atoms are the oxygen, so it's showing you two oxygens to every carbon, and that's what carbon dioxide is. So anyway, let's take that away and let's have a wee think about our results. Now, if we think of our results, and the first experiment I did was the grapes, and what I predicted, and I'm going to explain why, was that the grape that was peeled, because it was sort of bumpy like this, and the other one was smooth, I thought the bumpy grape had more space. And if you imagine, if you would sort of drawing all the way around that, because it's bumpy, there's more ins and outs, and it would take up more space. So I thought, because there was more space around that, there was more surface area. Because there was more surface area for the carbon dioxide molecules to go on, I thought that the peeled grape would rise to the top quicker because there was more carbon dioxide in it. So that was my prediction. Let's make that a bit neater. Peeled, that was my peeled grape. And I thought it had a greater surface area for carbon dioxide. That's how we write carbon dioxide. The carbon with two oxygens, and then my unpeeled grape, I thought had less surface area, and I thought that's what would make the difference. So I thought that this one, the peeled grape, this one here, I thought would dance more because it would go up and down faster as more carbon dioxide went on it when it was at the bottom, and then popped when it got to the top, so it would sink back down. However, that is not what we found. When we did the experiment, we actually found that the unpeeled grape, this one here, sorry, the peeled grape, beg your pardon, the peeled grape No, I'm getting mixed up here. I was right first time. The unpeeled grape, this one, the unpeeled grape, was the one that actually danced more. Now, I had to think about this and had a chat with Mr. Richmond, and a pair of us have decided that the reason for this, yes, the peeled one might have more surface area, but we think he's right. We think that if you take the skin off of a grape, what happens is the peeled grape inside is acidic, we think. So although there is more surface area, slightly, because it's got more ins and outs, and in theory there should be more space for the carbon dioxide molecules to go on, or the carbon dioxide to go on, we think as soon as the carbon dioxide went on the peeled grape, as soon as the carbon dioxide tried to go into it, it actually popped. And it popped and it didn't stay on. But whereas when the carbon dioxide went onto the unpeeled grape, it stayed there. And we actually saw that when we watched the experiment. This is exactly, I know it's not a very good drawing, but we saw that the unpeeled grape, the normal grape, had lots of the air, it looks like air, but it was carbon dioxide bubbles on it, whereas the peeled grape had none at all. And we think that's something to do with acid. That's what we think. So what we saw there, what this experiment showed, I suppose, was that because the carbon dioxide didn't adhere to the peeled grape, it didn't stick in the peeled grape, then that it is the carbon dioxide that was causing it to rise up and fall down, because it didn't go on that and it didn't allow it to rise up and then fall back down. So I suppose that's all that one showed. I did think it would show something about surface area, but it didn't. It'd be interesting if any of you else, if you do that experiment, whether you get the same results. Will you get the same results as me, that if you peel a grape, the carbon dioxide can't go in it, because of the acid changes it somehow, and it can't actually just stay on it, and carbon dioxide bubbles, so the peeled grape doesn't work. It'd be interesting to see if you get the same results. So that's what we think is happening with that one. Now, if I could drop this out, and if we think of our second, or my second experiment, was if you remember right, that was the cranberries, and the cranberries, we tried lemonade and we tried fizzy carbonated water, and that's why it's called carbonated drinks, boys and girls, because carbonated means adding carbon, adding the carbon dioxide. That's why they're called carbonated. So at my experiment, I tried to have the same amount of liquid. I tried to have the same size and type of things I was in it, but just one of them I had fizzy water, and one of them I had fizzy lemonade, one of the beakers, and I was seeing whether my cranberries danced more in the fizzy water or the lemonade, and I was taking that, and the one that they danced longer in, I suppose, was the one I thought had more carbon dioxide. Now, when I started the experiment off in the video, it looked as if the lemonade was working better. Remember, the cranberry in the lemonade actually started going up and down first, I think I remember right. But what we actually found when we kept the experiment going, the cranberries in the fizzy water kept going much longer. Now, you didn't see that because we stopped the experiment, but I watched it, and the cranberries in the fizzy water kept going down to the bottom, kept getting the bubbles of carbon dioxide on them, and kept rising back up to the top, whereas the cranberries in the lemonade actually stopped dancing quicker. Interestingly, they took a while to sink down to the bottom, because I think cranberries are actually a word that the Cirque video used, are actually more buoyant than raisins, and buoyant just means how well you can float, and it depends on the density. Now, I actually know I did some work in the past couple of years, actually, my classes with density, and we should know density is really how heavy you are for your size. So, yeah, I think this experiment I did show, we did get a result. This experiment, my prediction was, I actually can't remember what my prediction was, but the result we got was that fizzy water seems to contain more carbon dioxide than lemonade. I actually think I predicted the other way. And the reason I'm saying that is because the cranberries kept dancing longer, much, much longer in the fizzy water than the lemonade. And I actually looked up online, I looked up Google. Now, remember, Google's not always right, but I did look up and I tried to find out how much carbon dioxide was in different drinks that you buy. And I found out actually that carbonated water and soda water and things like that actually do contain more carbon dioxide than lemonade or Coca-Cola, which kind of backs up to what we found. So that's us, boys and girls. That's our results finished.